now that we've discussed the fundamental theorem of calculus, and we know that a faster way to evaluate a definite integral is to use its antiderivative, that means we need to further expand our ability to find antiderivatives. As we saw, the Riemann sum works, but it's limited because it's based on the summation formulas. We are limited to only doing the Riemann sum for a polynomial of degree 3 or less. Any other type of function, the Riemann sum doesn't work with the summation formulas, and the only other option would be to do it numerically, to use increasing specific values of n and evaluate it, well, honestly, by hand, which is an excessively painstaking process if we're doing it by hand. So we really need to be able to find antiderivatives. Now, what we know from derivatives is that there are several different techniques for finding a derivative depending on the nature of the function. For example, if we're looking at just a straight polynomial, we could use the sum and difference rules and the power rule to isolate each term, and to use the power rule to then integrate each polynomial term. But if we're dealing with something that is, say, a product or a composition, well, then we needed a special rule for it. Well, integration is no different. If we're dealing with a product or a composition, we need a special integration rule to deal with it. So the first of these that we're going to look at is integration by substitution. Integration by substitution is the inverse of the chain rule for derivatives. So it starts with the idea that if we want the derivative of a composition, we need to do the derivative of the outer function composed with the original inner function times the derivative of the inner function. The integration version of this has to turn it around, which means that we need something that is in this form to begin with. So for integration, we need something that is in the form of a composition and already has the derivative of the inside function present as a factor in the integrand. And then if we do it properly, we should get the antiderivative of the outside function composed with the inside function, of course, plus the constant of integration. So the trick here is that what we are looking for is an integrand that has, first of all, a composition, and secondly, that has attached to it times the derivative of the inside function. Now, when we did the chain rule, we learned how to use a u substitution. Let u equal g of x. Take the inside function out, and that would allow us to differentiate the inside function, and separately from that, differentiate the outside function. It allowed us to treat this as not as a composition, but as two separate functions and work with each of them individually. Well, we can still do the same thing here. The difference is that when we differentiated, we needed to produce g prime of x as part of the derivative. When we're integrating, we need to recognize that it is already there. So in either case, whether we're differentiating or integrating, we still need to find the derivative of the inside function. So we're actually going to address these problems the same way that we did the chain rule, in using a U substitution, rewriting the composition using U instead of the inside function, and differentiating the inside function. Now, unlike the chain rule, where we just have to then assemble the parts, we need to now, with integration, take those individual parts and rewrite the integrand. So what we're going to end up with here is that we have two statements that relate our new variable u with the original variable x. We are allowed to manipulate in any legitimate algebraic way. We are allowed to manipulate these two statements, these two equations, to replace all instances of x with instances of u. Now, what does that actually mean? Well, it really does help to see an actual function here. So let's take a look at one. Let's suppose we have the function x squared plus 1 squared times 2x dx. Now, what we have here is, first, a composition. We have the composition here, x squared plus 1 on the inside, with the square on the outside. So, just like with the chain rule, we're going to start out with let u equal the inside function x squared plus 1. Now, I'm not immediately going to turn to rewriting the integral in terms of u, because we do need something else as well. Du dx, which is, well, 2x. Easy enough to get. Now, the rule for replacing one variable with another is that you need, in a statement of equality that has one variable on one side of the equation and the other variable on the other. Now, the first statement, u equals x squared plus 1, already has that. The left side has u with no x's, and the right side has x with no u's. The squaring and the plus 1 are incidental. They are not a u or an x, so they can be wherever they need to be, but the important thing is that the u's are on one side, the x's are on the other, and there's no mixing of them. The second statement, however, does have a mixing of them. Now, the right side is fine, it just has 2x. But the left side has du and dx. We cannot have both the u and the x on the same side. So we need to fix that. And the way we do so is by multiplying both sides by dx. Let's not forget that du and dx are actually quantities. We never see them as such. We never see du equals this number or dx equals that number. But remember where they came from. Du dx is the instantaneous rate of change, which was the limit of the average rate of change. So the numerator of this fraction is the change in u, and the denominator is the change in x. If we're doing an average rate of change, we use delta u and delta x to represent a relatively large change in u or x. But when we apply the limit and get the instantaneous rate of change, what we're looking at is an infinitesimally small change in the value of u and an infinitesimally small change in the value of x. So du and dx are quantities. They are infinitesimally small changes in the values of those variables. And because they're quantities, we can definitely manipulate them algebraically as we would any other quantities and any other fraction. This is a division of du by dx, and we can undo division with multiplication. So this statement now becomes du is equal to 2x times dx. So let's take a look at what we've got here really quick. We have a statement here, u equals x squared plus 1. And up here we have an x squared plus 1, which can now be taken out and replaced with a u. We have another statement down here that says du is equal to 2x dx. And here we have a 2x dx. Well, if 2x dx is equal to du, then we can take those out and replace them with du. So based on these two statements underlined in blue, we can rewrite the integral x squared plus 1 squared times 2x dx. We can rewrite it as u squared du. Now, we have done everything algebraically correctly. All we have done is we created this new variable, and we replaced one, or in two different parts of the integrand, we replaced a statement with an equivalent expression. We replaced x squared plus 1 with u, and we replaced 2x dx with du. The result, then, is an integral that is considerably easier to integrate. By the power rule, we add 1 to the power and divide by the new power. Let's not forget our plus c. This is an indefinite integral. And just like with the chain rule, we have to remember that this u that we used is a temporary measure. We temporarily replaced the variable x with the variable u. At the end of the problem, we do have to go back to our original variable. Now, this is not the most obvious thing in the world. We have to trust the process. As with all things in math, this is a series of logical steps. If A is true, then B is true. Then if B is true, C must be true. If C is true, D is true, and so on and so forth. So we took the logical steps of letting u equal the inner function x squared plus 1, found the derivative of the inner function, and created a second statement, du equals 2x dx. So if we let u equal x squared plus 1, then du equals 2x dx. And if those two statements are now established, then we can use them to replace instances of x with instances of u. And if we have done that, then we can integrate. And once we've integrated, we can go back to the original variable. Now, this is easy enough to check. We can just check this by differentiating it. I mean, that's part of the idea of the first part of the fundamental theorem of calculus, to show that the antiderivative and the derivative are actually inverses of each other. So if we differentiate this, I'm going to write the denominator of 3 as a fraction of 1/3 in front to make our lives a little bit easier. Well, the 1/3 is a coefficient, so it just comes along for the ride. For the derivative of x squared plus 1 cubed, we would do the power rule, leaving the inside function alone, times the derivative of the inside function. And then the derivative of the constant of integration is, of course, 0. So what we have here is the 1/3 times 3 cancels out. The plus 0, no, there's no reason to write that. So what we have is x squared plus 1 squared times 2x, which was the original integrand. So this is the correct answer. We checked it by differentiating. This is the antiderivative of x squared plus 1 squared times 2x. Let's try some other examples. Suppose we have the indefinite integral of the square root of 2x plus 1 dx. Now, this, is, because of the square root, is something that we would not be able to do a Riemann sum for, unless we did it with specific values of n that get larger and larger, which, as we know, would take a great deal of time. What we can do here, though, is recognize that there is a composition. We have the expression 2x plus 1 underneath the square root. 2x plus 1, then, is our inside function, so we start out with let u equal 2x plus 1. That statement is fine as it is, because it has just u on the left with no x's, and on the right it has x with no u's. In that case, its derivative, du dx, would be, well, just the constant 2. Now, this step is going to happen every single time you do integration by substitution. You're always going to have to multiply both sides by dx here. That will happen every time because we need to get this statement into something that has just u on the left and just x on the right with, we don't want to see the both variables on the same side of the equation. Now, 2 is incidental. It is neither a u nor an x, so it doesn't really matter which side it's on. And that's important because when we come up to the original integrand up here, we have 2x plus 1, which is equivalent to u. Now, what we did in the previous example was we had the 2x and dx both get replaced by du. The problem here is that we have a dx, but I don't see a times 2 in there. Well, that's actually not a problem. The basic idea of using these statements is that everything on the side with the x is going to come out, and everything on the side with the u is going to go in. So if there's no 2, if there's no times 2 in the integrand to come out, then what we can do is divide both sides by 2 and manipulate this statement a little further so that it becomes 1/2 du equals dx. If there's no times 2 to come out, then we can put in a 1/2. And again, that's what is meant by manipulating these two statements. That as long as the u's are on the left and the x's are on the right, anything else can be on either side, depending on whether it's present and coming out, or whether it's not present and needs to go in. So everything with the x's, on the side with the x's, is coming out. Everything on the side with the u's is going to go in. So what we've got here then is that the antiderivative of the square root of 2x plus 1 dx can be rewritten as the antiderivative of the square root of u times 1/2 du. So again, the 2x plus 1 comes out, and the u goes in. The dx comes out, and the 1/2 du goes in. From this point, integrating it should be relatively easy. We can do a few things, like bring the 1/2 out in front, and write the square root of u as u to the 1/2, so that we can use the power rule. So we have the 1/2. We add 1 to the power and get u to the 3/2 over the new power 3/2 plus c. Now this looks horrendous and disgusting, and to be honest, it's not the nicest thing in the world, but it's not too awful. Rather than write division by 3/2, we can rewrite that as multiplication by its reciprocal, 2/3. And then we get a little bit of simplification there. So what we're left with is 1/3 times u to the 3/2 plus c. And finally, we'll put our 2x plus 1 back in for u. And once again, you can easily check this answer by integrating. By differentiating. I'll leave that to you to do, and assure you that we have done this correctly, and that is the correct result. Now, there are other variations of this that may occur. Let's take a look at another example here. Suppose we have the antiderivative of x over the square root of 3x minus 2 dx. Well, we can see the composition, like before, of 3x minus 2 under the square root. So let's start with that. Let u equal 3x minus 2. Therefore, du dx is equal to 3. And with our usual multiplication on both sides by dx, this becomes du equals 3 dx. Now, let's examine what we've got here. We've got the statement u is equal to 3x minus 2. So our 3x minus 2 in the denominator here is going to get replaced by a u. Now, as far as the du equals 3 dx, we have a similar situation as to the last example, where I don't see a times 3 up in that integrand. There's a dx, clearly, there always would be, but I don't see a times 3. So, much like we did in the previous example, if there's no 3 to come out, we can manipulate this equation so that we put in a 1/3. So now we have 1/3 du equals dx, and that means this dx can come out and get replaced by a 1/3 du. Now, there's one conspicuous thing here, and that is the x in the top. We've managed to take out both of the other places where we see an x, the 3x minus 2 under the radical in the denominator. That x is coming out. The dx is coming out and getting replaced by 1/3 du. But we still have that x in the numerator. What are we going to do with that? Well, if we're allowed to manipulate the du dx equation by multiplying on both sides by dx or dividing on both sides by 3, then we can also manipulate the u equation. Again, the 2 and the 3 up here are neither a u nor an x, so they can be moved around as needed. So what we can do here is add 2 to both sides and divide by 3. And we can get a statement that instead of u equals 3x minus 2, we have 1/3 u plus 2/3 is equal to x. And this statement can now be used to replace the x that was in the numerator with 1/3 u plus 2/3. Not pretty, not ideal or as clean as the last couple of examples, but it certainly can be done, and it works. So let's take our integral, x in the top, square root of 3x minus 2 in the bottom, dx, and let's rewrite it in terms of u. The numerator now becomes 1/3 u plus 2/3. The denominator now becomes the square root of u, and the dx becomes 1/3 du. Well, again, it's not pretty, but from here, we can certainly make this work a little bit nicer. We can clean it up a bit. First of all, we can take the 1/3 here and bring it out in front of the entire integral. In the denominator, we can rewrite the square root of u as u to the 1/2. Now, the numerator is a little bit ugly because of those fractions, but I'm going to leave them for now because what's going to happen with the u to the 1/2 in the denominator is it's going to distribute underneath each of the terms of the numerator. So it's going to become our 1/3 out front. We're now going to have 1/3 u over u to the 1/2 plus 2/3 over u to the 1/2 du. In the first term, we can simplify the u in the top with the u to the 1/2 in the bottom, and it becomes 1/3 u to the positive 1/2. In the second term, what we can do is simply move, since there's no u in the top, we can simply move the u to the 1/2 up and make it u to the negative 1/2. And in this way, we can use the power rule on both of these. So we have the 1/3 in front of everything. We now have the 1/3 in front of this first term. And when we add 1 to the power, it becomes u to the 3/2 over 3/2. In the second term, we have 2/3 in front. And when we add 1 to the power, it becomes u to the positive 1/2 over positive 1/2. and then we'll have a plus c at the end of the whole thing. So again, this is just a matter of cleaning it up. I'm going to leave the 1/3 in front of the whole thing for the moment. We have 1/3. Instead of dividing by 3/2, I'll write it as times 2/3 times u to the 3/2. Here we have 2/3. Instead of dividing by 1/2, we'll multiply by 2/1 times u to the 1/2 plus c. So again, we'll keep that 1/3 out in front for now. We'll deal with that in a little bit. But we can at least combine the coefficients. 1/3 times 2/3 is going to give us 2/9 times u to the 3/2. And in the second term, 2/3 times 2/1 would give us 4/3 u to the 1/2. So we have 1/3 in front. And then 2/9 u to the 3/2 plus 4/3 u to the 1/2, and then our plus c at the end of the whole thing. So one more step to distribute that 1/3. That gives us 2/27 u to the 3/2 plus 4/9 u to the 1/2 plus c. And to finish the whole thing out, we put the 3x minus 2 back in for u. Now, this is ugly. It certainly doesn't look like what we might have expected, given the original problem. The original integrand, remember, was x over the square root of 3x minus 2. I think you'll agree this certainly doesn't look anything like that. It doesn't even look like a fraction. Well, if you want to, take the time to differentiate this and simplify it and show that it does turn back into the original. I certainly encourage you to do that to verify for yourself and make sure that this is working. But we've gone through a few instances of this now, and I'm going to assure you that this is the correct result. And that's something that we have to get used to, is a lot of these results of our integration are going to look very little like what the original integrand looked like. So we have to trust the process, or you have to take every answer you get and differentiate it and manipulate it until it looks like the original function. I think at this point we're going to have to trust it, because I doubt most of you will differentiate every single one of these answers to check it. So that means you're implicitly trusting the process. So let's make sure we got it down right. Now, how does this work with a definite integral? Well, actually, it works out just fine. We just have to separate, as we saw with the fundamental theorem, we have to separate the steps of finding the antiderivative from evaluating the definite integral. So let's suppose we have the definite integral 0 to pi over 2 of sine of 2x dx. Well, if we want to evaluate a definite integral, the first thing we need is the antiderivative. So really, we're just going to remove the limits of integration so that we can focus on the antiderivative, and now we can say, hey, look, we've got a composition here. Let's try it out. Let u equal 2x, so that du dx is equal to 2. Our customary multiply on both sides by dx. And like often happens, I don't see a times 2 in the integrand. This times 2 is already being taken care of by getting replaced by u. I don't see another times 2. So, since I don't have a times 2 to take out, I will manipulate this one more time and put in a 1/2. So our integral of sine of 2x dx is going to be rewritten as sine of u times 1/2 du, where, as usual, the constant multiple 1/2 can be brought out in front of the whole thing and give us 1/2 times the integral of sine of u du. And that's easy enough to integrate. The antiderivative of sine of u would be negative cosine of u. And of course, our plus c. We can rewrite this as negative 1/2 times cosine of 2x plus c. And that is our antiderivative. We are not done because now we need to apply the fundamental theorem of calculus. The fundamental theorem then says that the integral, the definite integral from 0 to pi over 2 of sine of 2x dx would be equal to its antiderivative, negative 1/2 cosine of 2x, evaluated at the limits of integration. Now, you'll notice I left off the plus c. As we know from dealing with the fundamental theorem of calculus, that plus c is the same when we are evaluating at pi over 2 as when we're evaluating at 0, and therefore will always cancel out. So when we are evaluating the definite integral, we can leave off the plus c. It is part of the antiderivative. It makes the general antiderivative formula, and we cannot determine the exact value of c without knowing an initial value. But the fundamental theorem here for the definite integral says we don't actually need to know that initial value. We can just leave it off. So let's finish this out by evaluating it. We have negative 1/2 times cosine of 2 times pi over 2 minus negative 1/2 times cosine of 2 times 0. Well, 2 times pi over 2 is pi, and 2 times 0 is 0. From the unit circle, we know that the cosine of pi is negative 1, and that the cosine of 0, the cosine of 0 is positive 1. So negative 1/2 times negative 1 gives us positive 1/2. Negative 1/2 times positive 1 gives us negative 1/2. And what we have here is 1/2 minus negative 1/2 is 1/2 plus 1/2. And that gives us 1. So the definite integral from 0 to pi over 2 of sine of 2x dx is equal to 1.